Good afternoon and welcome to the webinar, Why Excel is Failing Your Tolerance Stacks. This event, brought to you by Quality, is sponsored by DCS. I'm your moderator, Daryl Sealand, Editorial Director of Quality. Thanks for joining us. Today's presenters are Gary Bell and Brenda Quinlan. Brenda is Senior Dimensional Analyst for DCS. Gary is a dimensional engineer with more than 15 years of experience working for DCS, specializing in GD&T and dimensional management. Gary received his degree in engineering from Wayne State University, as well as becoming a senior-level ASME certified instructor. With DCS, he has successfully completed many projects for major companies in the automotive, aerospace and defense, medical device, and electronics industries. As the senior instructor at DCS, Gary has been instrumental in delivering instruction and expertise to both DCS customers and employees. Don't forget to submit your questions, and later in the program, our presenter will address as many as possible. Today's event is being recorded and archived on qualitymag.com. And now I'm excited to turn it over to today's presenters, Gary Bell and Brenda Quinlan.
Hello, everybody. This is Gary Bell. Thank you for joining me today. Today, we're going to discuss and show the effects of 1D tolerance stacks, 2D tolerance stacks, and 3D tolerance stacks, and why we would recommend you go directly to 3D tolerance stacks. Our agenda is to show and discuss a little bit about 1D, show the difference between one-dimensional and three-dimensional tolerance stacks, show you I feel like a very cool, simple model in our 3D software depicting the differences between 1D and 3D. We're going to discuss a little bit about worst case and root sum squared analysis, or RS, otherwise referred to as RSS. And then we'll go into a little more realistic model, but still a not 100% realistic model to show you the effects of how three-dimensional tolerances interact with each other. And we will end it with a Q&A session. So what is worst case? Worst case tolerance stacks are when you set all of your tolerances to their min or max extreme that produces the maximum output on your assembly variation. It's the only way to guarantee that your assembly does not exceed its assembly specifications. However, if you design a product to satisfy worst case analysis, you're bound to tolerance your parts way too tight and make your assembly cost more than it probably needs to. So we're going to just focus on a simple 3-block assembly. And you can see here, if I have 3 blocks, 10 plus or minus 1, 7 plus or minus 1, and 12 plus or minus 2, this is a simple stack. We can just look at it and see that, okay, the minimum dimension, if we were only looking at it in one dimension, left and right, the minimum value would be 25 and the maximum value would be 33, making my variation, worst case, 29 nominal plus or minus 4, or 8 millimeter range of variation. However, when you do that one-dimensionally, you can't take into account the fact that if there's any orientation tolerances or form tolerances, how your assembly will react when it's tipping and rocking. So as you see from this picture here, you could have a minimum that could be less than your minimum stack as it folded in or out. So What are some of the shortcomings of 1D stacks? Is it does assume your tolerances are all have a one-to-one relationship to your measurement, and it doesn't take into effect any of that angularity or geometric effect from how your components locate to each other. And when you're doing 1D stacks, you pretty much have to stack your product in all three directions anyway to confirm that everything is going to be within its dimensional specifications. So we should just go ahead and do a 3D stack automatically. So the advantages of 3D is it will capture the geometric effects and the angular variation. However, to do a three-dimensional tolerance stack on paper can be very rigorous, lots of trig and calculations. So we use a computer to do it to eliminate dimensional errors that can be made while you're trying to do your stack. One thing when you're using a Excel spreadsheet, you have to put in all of the inputs, and if you don't have the exact stack path, you may forget an input or two. When you do a 3D tolerance analysis with the CAD data, your opportunity to miss a tolerance stack decreases.
Just to reiterate, when we were looking at those blocks in a single direction, we could only make a single measure. But when we looked at the tolerances and how they affected the assembly of the part, when we included orientation and form tolerance, now we could see how the variation was affected in multiple directions.
Okay, so now this is a very cool cartoon picture. I'm going to jump over to our 3D tolerance analysis software and show you the effects or the differences between 1D and 3D. So this is our multi-CAD version of 3D tolerance analysis, which does not require any integration with a CAD system, and you would just load your CAD data into this platform, and then you can define how your components go together. You can tolerance your individual components and write measurements. This model is complete, and first thing I'm going to do is just hit deviate. So this is going to be an example of showing you a 1D stack and a 3D stack. If you look at the left, you can see these blocks. They're just growing and shrinking equally, independently, but equally. When you look at the right, you can see that bottom surface is tipping and rocking. So instead of just a linear tolerance, that surface has got an angularity and a form variation on it. You define how these components go together with moves, which you can see here. And that allows us to actually watch the build process. Oh, I did do it. Separate. I'll try this one more time. Give me 1 second. So in the separated position, you saw the components deviating. That was their piece part tolerances. And then when I deviated after it's built, now you can get a feel for, a 1D stack and the same parts and how it would react in 3D space. This model has got measurements. So you can see we're measuring from the base up to the nose of my smiley face, both on the 2D stack and the 3D stack. We're measuring it in the Z and the Y and the X. Z, Y, X.
Yeah. So just to clarify, the first red model represents a 1D stack, and our blue model represents a 3D stack because we see the effect of the tolerances in all three
directions.
Mm-hmm.
So once you have your 3D model complete, you can build it and run an analysis. We're going to go ahead and build 10,000 smiley faces. And you can see, oops, that's not what I wanted to do. Why does that keep doing that?
It wants to auto scale on you, I think.
I noticed that. I don't want it to auto scale. So you can see we're showing you the contributors, 1, 2, 3, 4, 5. These are the tolerances that are in the model. So it's a 0.5 millimeter tolerance on each one of these blocks. But in a 1D, then this is going to get added up. A straight stack, my range of variation would be 2.5, where you just added these numbers up. Statistically, my range of variation is 1.12. If I go to the Y measurement, you can see in my 1D stack, I have 0 variation in the Y and 0 variation in the X. However, when I go to my 3D, now you can see, because this thing is swinging around in space, it's not even a normal output curve. And my range of variation based on the distribution is 2.1 millimeters. And now you can see down here how you have many contributors from all the points varying independently, 0.5, 0.5, 0.5, 0.5.
I think it's important to note we have a significant mean shift. So even though none of the tolerances have a mean shift, the output does.
That's what you're seeing right here. Mm-hmm. And then, of course, because this is varying through 3D space, when I measure in the Y direction, you can see I'm getting Y variation, mm-hmm. and I'm getting X variation.
Yeah, I'm just going to jump in here and mention that we're actually using a Monte Carlo analysis method rather than an additive method, because this better captures the unique relationships in each model.
Especially when there's interactions between variations. Okay. So let's talk about 1D versus RSS. With that simple model that I just showed you, we are adding up the normal distribution of the tolerances on each of the parts. That is referred to as root sum squared if it's truly just linear. And that gives us a statistical variation, which will not be worst case. However, it will allow you to have larger tolerances and not exceed your required variation, but you will have to account for a percentage of failures. As it shows down here, if you do statistical analysis, you do carry a risk of having some bad assemblies, but the probability decreases, and that's why we want to do statistical tolerance analysis. If we look here, these are the tolerances on the same, three parts, 10 plus or minus 1, 7 plus or minus 1, and 12 plus or minus 2. We saw earlier, if we added that variation up straight stack, we get a range of 8 or plus or minus 4. That's what you're seeing from here to here. If we assume that each tolerance is varying independently with a normal distribution, then when you added these up based on root sum squared, you would get a range of 4.88 at the 6 sigma range. This is including 99.73% of your possible variation. So that means you do have 0.13% failure on the tails. So with 3 separate tolerances, and if we look at just one side, failing 0.13%, the probability of failure is 0.0022% for one side. So let's talk a little bit about what is root sum squared. Root sum squared is where we're adding these numbers, we're squaring the input tolerances, and we're taking the square root, and that's where you're getting this 4.88. So when I was showing you that 1D stack on the left side of the worm model, because it was 1D and all the tolerances were normal, I didn't even need the software to calculate that. I could have just used this equation, 0.5 squared times 5, square root of that, and that would have given me the same number that the software gave us. However, if you have different distributions, a right skewed distribution, a bimodal distribution, then, as Brenda mentioned, we would have to go to random number Monte Carlo generated variation, and that's why we build thousands of simulations to get our statistical output. So now I'm going to jump over to a model that is a little more realistic. And this is our 3D tolerance analysis embedded into CATIA. So now you can see I have the actual CAD parts, and down here is where we still have the moves that define how these parts go together. We have measurements, what it is we want to analyze. And with this model, I'm just going to show you that we want to know what the gap is between this turn lamp and headlamp. There's moves here, so we can build this one move at a time. And we can hit deviate, and you can see this thing is jiggling around. Before I actually get to that results, I want to zoom in so that you can see this mesh, and you can see the GD&T that's applied to these surfaces. If I hit deviate, you can see the hole is changing in position, and the surfaces are varying due to all the GD&T. And here's a piece part surface tolerance on the headlamp and a surface tolerance on the turn lamp, 2 millimeters. So in the separated position, you're seeing piece part variation being applied to the components. And when you build it, you're seeing how the parts are jiggling around because this part is locating to the bracket and this part's locating to the bracket. And so now we're getting the accumulation of our component part tolerances and how the parts assemble, which is producing our tolerance stack. Now, to show you the effects, if I was to analyze this gap, 1D, so in this view, if I'm only looking left and right, first I got to tell you that the turn lamp, locates with these pins going into these holes, and the headlamp locates, this pin is setting the headlamp up, down in the Z and the Y, and this is setting the headlamp in the Z.
Sometimes we call them a 4-way hole and a 2-way hole.
Yes, and I have a habit of saying up, down, fore, aft, cross, car, because that's automotive. So I tried to switch it back to XYZ. So if I want to know this gap, if I'm doing it in a 1D fashion, I don't get to account for both of these tolerances unless I want to trig out and calculate how much, when this moves up, how much does that make this move in?
Well, that would make it a 2D stack, Gary.
Yes, that's true. I can't.
When we're constrained to 1D, we can only look at one direction. We can only look at the first DA hole or the 4-way hole.
Right. Thank you. So if I'm looking at, this is why I bring her along, keep me on the straight and narrow. So for me to calculate this gap in the Y direction only, I can go from this surface to this locator, to this locator, to this surface. That's it. If I tried to include the other locators, that would be a 2D stack. So that's what we did here. As you can see, my move is only using those two locators. So when I do a nominal build and I'm going to run an analysis, well, actually, before I run an analysis, if we come in here and we deviate it, you can see how this is just moving back and forth and up and down. There's no tipping and rocking in this gap. You don't see any angle variation. And if I look at it in this view, you can see it's only moving back and forth. There's no X variation. So if I build it and I run an analysis, sorry for those loud beeps, I'm overwriting old data. Then you can see that it's predicting that this gap is going to be 3.42. And the only causes of variation that we have is actually, I like to show it here. You can see we have the surface tolerance on the headlamp, the surface tolerance on the turn lamp.
And those are on the measure surfaces themselves.
Correct. And the position tolerance on the bracket that's controlling this hole and this hole. So from a 1D analysis, if all I was going to do was a 1D stack, I would predict that the variation would be 3.42. And then, of course, if I wanted to do a worst case, I could just add all that up, which would be 6. So I'd have either a worst case range of 6 or a statistical range of 3.42. But that's not going to be accurate anyway. So now I'm going to switch this over to a 2D stack. So now, if I click on this move here, you can see I am utilizing this 4-way and this 2-way, but I specifically made sure that these moves are not going to pick up any of the surface tolerances. So this is actually turning this into 2D. So when I build it and I deviate it from here, now you can see how the gap in between the headlamp and the turn lamp is opening and closing, independently at the top and the bottom, because this part is tipping and rocking. However, I still have no movement in the X. So this is a 2D analysis. And if I build it, run the analysis again, here comes 2 beeps.
So if you wanted to do this 2D analysis in Excel, you would have to sit down, measure a bunch of dimensions between the locators and the measure surface, do a bunch of trigonometric calculations to get the ratio of effect between the tolerance and measure. In DCS, we call that a geometric effect, or a G factor, and then calculate your estimated range from each tolerance, then sum them up using the RSS or possibly worst case method.
So here you can see my variation increased. It went up to 4.31, and my causes of variation, now all of a sudden the surface profile tolerances, which are right on my measurement features, they're not even the number one contributors anymore. But now you can see there's my four-way locator, surface locators, or surface tolerance, four-way locator on the headlamp, and then you have your two-way locators. So now the variation is increasing because we did take into account the variation of this hole and slot, and we took into account the variation of this hole and slot, which is causing this to tip and rock. This is a clearance hole.
Not only do we get a more accurate upper gap measure, but now we can make multiple measures at once and check the bottom gap and check the parallelism of the gap, or what we sometimes call the AV measure.
Yeah, so Brenda is correctly taking me out of just the first measurement, but if you see a 1D study, you have to do a whole bunch of single 1D studies. With a 3D tolerance analysis, once you have this built, everywhere you write your measurements, that's going to be picked up. So this has got an upper gap measurement, a lower gap measurement, minimum gap measurement, and the AV gap. The AV gap measurement is just us taking this gap and subtracting it from this gap. And because these parts are located differently, this has got a four-way locator here and a two-way locator here, where this has got a four-way and a two-way here, the geometric effect up here is going to be different than down here. So when you look at my upper gap and my causes of variation, I have 4.31 millimeters of total variation. If I go to my lower gap, the lower gap isn't varying as much. That's because this is hanging out here farther from its locators than this one. Hence a lower geometric effect. So this variation is different and the contributors are different. So the gap down here, the top two causes of variation are the profile tolerances on the two features. But as you get up here, the position tolerance on here starts becoming a key factor. And that's all depending on your three-dimensional design, how these tolerances are going to interact. And then the AV gap is just subtracting the two. So now I showed you at the beginning of this model that I also have tolerances on the surfaces. So you can see these surfaces are all moving. Yeah. So now if I turn on my 3D move, give me a second, having control and alt control. There we go. Now I'm locating to these surfaces which have tolerances. So when I build this and I zoom in and hit deviate, we'll slow it down a little bit. Okay, now you can see besides it tipping and rocking, opening and closing this gap, it's tipping and rocking in the X direction. So now I'm picking up all the true variation due to X, Y, and Z variation simultaneously. So when I build this and run an analysis, you can see my gap at the top increased even further. And the real kicker here is that the number one cause of variation is the surface profile on the bracket. So this is an example where if we were worried about the Y gap between the turn lamp and the headlamp, we would have to know that the number one cause affecting that gap is the surface tolerance on this flange right here, which is varying in the X direction. So if I put it in this view here and I say deviate, yeah, an X tolerance here is the biggest cause of a Y gap here. And you can visually see how the headlamp and turn lamp are tipping and rocking. And now, of course, so now you have a surface profile. If we look at a 3D model, let me separate this.
3D tolerance analysis is really good at picking up and bringing forward these kind of non-intuitive relationships. You know, when you're doing a tolerance stack in Excel, you think of what all the contributors are and write them down. When you do a 3D tolerance analysis in a software tool, you define the known information, the assembly process and piece part tolerances, and the software finds out what each relationship is.
So now if we go through the contributors, we are looking at this gap in the Y direction only. Number one contributor is an X tolerance. Then we have the four-way locators, which is Y and Z. We also have the Z tolerance on this slot over here, as well as the Y tolerance on the actual surfaces that we're measuring between. So this is a great example of, we want to know a Y variation, and it's a function of X, Y, and Z tolerances. And if I stop sharing and go back here, this was just a summary of that basic model, where you can see the original 1D variation was 3.42, the 2D variation was 4.31, and the 3D variation was 5.26.
So not only, do we get, a more accurate result, but I don't think it can be said enough that when you have, 100 outputs to generate for your assembly, it's so much easier to make a single model and generate the results for all 100 measures at once than to sit down and make 100 Excel stacks.
Yes, that's going to lead me into, since it looks like we have a little bit of time, once you have your model done, if you wanted to add another stack, well, I can do that simply by writing a measurement. And so I'm going to say I want to write a measurement after the assembly. So I'm putting it at the top. I'm going to say point distance measurement.
Oh, Gary, you haven't shared your CATIA.
Oh,
yeah, can I share your screen?
There we go. Let me back up.
Should we mention that Gary's showing this model in the CATIA embedded platform?
We did.
Okay, so.
That was a good catch. This is where it happens. I'm going off script.
Yeah.
Okay, so now what I wanted to show you is, let's say the model's done and somebody says, well, how much is the tip of this headlamp varying in the Z direction? All right, well, I can do the Excel and I can say, well, I have to account for this tolerance up here, and it's got to go through this hole, and it's got to go through this hole. Or I can just go in and say, I want to write a measurement. I want to put that measurement in the final assembly. This isn't 100% complete, but I'm just giving you an idea. I'm going to say headlamp Z variation. I'm going to just pick this point that's up there. And I'm going to say that I want to measure it in the Z.
When you're done with this, Gary, I have a question I wanted to answer.
Sure. And I say, okay. And now there's my new measurement that I wrote. And so I can build this again. And I'll run another analysis. I'll go backwards, and there's my Z measurement. And you can see, because I didn't put the tolerance on this top edge, that it's saying, hey, the number one contributor, let me separate it, is the four-way locator, then this X surface tolerance. And there's some more locators here, but we have the software set up right now where it only shows you. I'll go ahead and turn them all on.
Yeah, Gary's showing a model where we've created the GD&T. So we only created call outs where we plan to measure. But if you happen to have PMI data with GD&T defined on all of the relevant surfaces, you can extract that and bring it into your model with just a button push and some validation to make sure the variation is doing what you expect.
Yeah, so that's, as Brenda was mentioning, you will do a 3D model, and once you define your part tolerances in your assembly method, you can have, unlimited measurements, and each measurement is essentially an Excel stack. Okay.
So we actually have a tool in 3DCS that will do 3D stack analysis where it calculates that ratio between each tolerance and measure, that G factor, and will give you an RSS and a worst case stack. But we've been showing you Monte Carlo analysis because that lets you bring all kinds of conditional effects, lets you build things in an iterative state, basically put in algorithms in your assembly process. And you can do all kinds of things like if you had torque that you wanted to model and you knew as the part was being assembled, it was going to twist in a certain way with the pins and holes, you could apply that. And so as the sizes of those features vary in each build, it would twist a different angle amount. Same thing with a gravity effect causing the part to drop down. Right now we've been showing you all rigid bodies, so all of the parts that you've been seeing have been perfectly rigid. But if you had FEA data available for those parts and you wanted to model things like deformation as the parts are clamped and joined together, you could bring in the FE data and actually distort the parts build by build and show things like forces on a part and gravity on a part.
Do you want me to show them geofactor? Yeah. Okay.
Yeah, you want to show geofactor for 1D versus 3D?
We have a lot of engineers and advanced people on it, so you can go deeper.
So we talked earlier that, hey, if you're locating here and here, the variation on this here is going to have some kind of geometric effect on this corner. And even worse if I'm locating with these two pins on this corner out here. So we have, I'll go to the 1D, I guess, first and see what happens. I'm guessing geofactor is going to be nothing.
Well, it's gonna match what you would get in a 1D tolerance stack.
Yes.
So it's really just a validation, like our geofactor tool, makes sense.
So when you're creating this model, you're basically working your way down this right-hand side, writing moves here, tolerancing your parts here, and writing measures. You saw me write a quick measure using this button here. These are all your graphic animation that, we separate, build it, deviate it. And then when your model's done, I ran this button here, which was a Monte Carlo analysis. Actually, I'm going to do it again so that I have the numbers sitting there.
You could also, no, never mind. If you had given your files different names, then you could have brought it up.
Yeah.
I digress.
So now I'm going to go ahead and run this analysis, which is geofactor analysis. I did have just the 2 point, yeah, okay.
Yeah.
So you can see that geofactor analysis is calculating 3.4 millimeters of variation, which is matching the Monte Carlo analysis, and it's giving you the estimated worst case range, 8.55.
And all of our geometric effects are approximately 1
because we're only varying this headlamp and turn lamp left and right.
Yeah, when you do a 1D stack, you're looking at a 1-to-1 ratio.
So now, I should have, I'll change the names. Okay. Now I'm going to go back to the 3D. Now I'm going to build, run an analysis. This will stay up here.
Yep.
Anyway, so
you can have a histogram with the 1D moves and a histogram with the 3D moves.
So here you can see, okay, 1D 3.42, 3D 5.26.
Yeah.
My contributors are all different here, but let's run geofactor. So geofactor, this is what we're looking for. So you still have, you can see my estimated range is 5.23. That's, pretty much the same as my Monte Carlo range. My estimated worst case range is 16.9. And this is what you want to know. This is where we're already calculating for you that, hey, this surface profile tolerance on the bracket on this CAD surface number 3, it's a 1 mil tolerance, but it's being amplified based on how these parts are indexing to each other. And on this upper gap measurement, it's acting like a 2.35 millimeter tolerance.
When the magnitude of a G factor is greater than 1, sometimes I call it a cantilever effect.
Mm-hmm. So you want to use your 3D tolerance analysis, one, to pick up all your contributors. And then with geofactor, if your G factor number is greater than 1, then you may want to think about modifying your datums or your indexing features because your tolerances are being amplified due to how you're locating your part. So, sure. So,
Repeat my question.
yeah, one of the things that came up was how is the model built? As I mentioned, you have to define moves, and if you look, when I did a 1D move, I was essentially locating this turn lamp with just this pin in this hole. Okay. Most parts you're not going to. That was me cheating the system. That's me turning a 3D model into a 1D model, which, I had to digress to do that. What I want to show you is how the model really locates. And if we look at this turn lamp, then or headlamp, if I go into the actual move, this is what's called a 6-plane move, which is based off of a 3-2-1 locating system, primary, secondary, tertiary. And if you look, I'm just selecting objects to locate to targets. So it highlights everything in the move. So it's telling you, hey, I'm moving the headlamp, and I'm moving the headlamp utilizing these features, and it highlights them on the graphic. So if you see, I have a 01, 02, 03. So those 3 points are locating to a T1, T2, T3, for the primary plane to locate this in the X direction, then this hole is my four-way locator, which is that pin, which is going into this hole. And then this pin over here is going into this slot. And we show you the directions of control. So you can see these vector directions. So this headlamp is located into the bracket in the X, here, here, and here. And then it's using this hole to control Z, this slot to control Z, and this hole to control Y. And so each of our parts is going to go through a move. That's why I can animate this one move at a time. Put the turn lamp on, put the headlamp on. And if you look on my list of moves, you can have multiple moves in your model. So I have 3 different moves on the turn lamp. All of them are different methods of locating the turn lamp, because I wanted to use a single model to show you the effects of if I located the turn lamp 1D, if I located the turn lamp 2D, if I located the turn lamp 3D. So the power of the software is I'm using it for 1D, 2D, 3D, but you could use it and have different assembly methods for your components in the same model and just turn your moves on and off as you analyze, which process is better from a dimensional standpoint.
Yeah, you could easily make a chart showing your measure results under different scenarios.
I have scenarios.
All right.
I don't know.
Oh, yeah. And to help you, there's a tool to help you organize them if you had a more complicated model. Gary, we've had a couple of questions about using joints and constraints. So everything you've been showing us has been using what I call a classic 3DCS move that uses a 3-2-1 type assembly definition.
Yes.
If you have a mechanism and that mechanism is built using joints such as revolute joints, planar joints, spherical joints, we can build that directly using those definitions in 3DCS using our mechanical toolbar. Either the modeler can define each joint according to how it's going to be assembled, or the joints and constraints can be created. Oh, Gary, you got a model ready to go.
I know. I got excited, except you can't see my GD&T. I got to change my background color.
Okay.
Tools.
So this model actually has the joints created in CATIA, and we extract
where? Oh, it's right here. Yeah. Sorry.
Yeah, we can extract them with a button and turn them into moves in the DCS software.
Yes. So if you see here, inside CATIA, these joints are already defined, as well as these constraints are already defined in CATIA, and you already have joints defined in CATIA. If this information is available, then in our software, you can just hit this button here and extract it, and then we will automatically build it. I'm not going to do that just yet. I want you to see this model first, so I will nominally build it.
Is the motion move active?
It should be. It's active, yeah. So this is now going through its range of motion, and it's including, I don't know if the GD&T was extracted yet, but it's at least, hold on one second.
Well, we can see some whole pin float on that yellow bar.
I'm turning, I think the tolerances, I already have the tolerances. Let me, I'm going to backtrack a little bit. I'm going to delete my GD&T on the base, and I'll go ahead and delete my moves. Just so everybody can see.
Yep. let's see.
So now when I hit deviate, you can see the only thing that's deviating on this base is a surface tolerance, a DCS surface tolerance. But you can also see that this base has got FTNA or embedded GD&T on it. Excuse me. And it won't build yet anymore because I deleted all my moves. So first thing I'm going to do is extract all my moves from CATIA. And it says, hey, it found 9 constraints or 8 joints and 3 constraints. If now I can hit nominal build and it builds, and I want to turn my mesh off because again, I don't know if I had other tolerances, but hopefully when I hit deviate, you can see that it's going through its range of motion and there's no tolerances on. I'm going to go back to my move list and find the revolute joint for the banana, this one right here. So we extracted it and we populate our own move here. Oh, why is that not floating?
It is floating, it's active.
I know, but I didn't see it float when I hit deviate. Oh, it's floating. Yeah. So you can see without tolerances, this is going through its range of motion from the joints and constraints that were removed or that were extracted from CATIA. And because this pin is smaller than the hole, it's floating around that pin. And so there's variation just nominally because the design, the pin is too small. And then if I turn my mesh back on and I hit deviate, you can see nothing's moving, but I see I have this GD&T. So I'm going to come up here and I'm going to say, hey, I want to update my GD&T. I'm going to pick this part and I want you to watch this base right here. When I pick the base, it says it found 15 GD&T callouts. It now populated the GD&T in the 3 DCS storage. When I hit deviate, you can see now these pins are moving around due to their position tolerance. And it's really crazy. You can see this surface down here, it's varying for profile, parallelism, and flatness. All 3 of them on that little pad surface. And of course, you know, this is large so that you can see things.
Exaggerated tolerances.
Thank you. Exaggerated tolerances. And if I build this now, I'll turn this off again.
So just a point of clarity, you know, with our rigid body modeling, you can only restrain 6 degrees of freedom for a part. So if you had an over-constrained part, you either have to drop some of the locators or use a fitting routine, like using a least squares fitting or some sort of conditional move. You have to bring, and we find that the least squares fitting is a pretty good approximation of what's going to happen in real life. But if you can bring in the FEA data, then you can get an more accurate result of what would happen with over-constrained parts. With the parts actually deforming to meet all of their locators.
So that was a good question, whoever asked it, that 3DCS can utilize embedded FTNA joints and constraints in CATIA. It can utilize embedded PMI and constraints in NX, and it can utilize embedded PMI and constraints in Creo. Thank you. And we are in the process of integrating into SolidWorks. We should have a beta version of that out this year sometime.
Good.
Oh, subdatums? Yeah, so our GD&T we've been showing you is pretty simple, just A, B, and C, and tolerances back to A, B, and C. But if you had different DRFs and you're using our GD&T tolerancing, you can capture all of the relationships between the datum features.
Yes. Before, I'm going to stop sharing. You can still ask questions,
We should go to.
but I want to go to this last slide.
See your contact information.
Yes, so that you see that if you have further questions, feel free to contact us and we will answer any questions you may have.
I was thinking, with CAD software, we went from, drawings to 3D models in a computer. And with variation analyst software, we can go from stacks on paper to variation analysis on an assembly.
To him for the last question too.
Please pass off.
Thank you very much, Gary. Thank you very much, Brenda. Again, if you have questions for Gary or Brenda, I'd kind of encourage you, based on their last slide, to reach out and they can answer questions for you. We are just about out of time, so I'm afraid we're not going to be able to get to questions here in the presentation, but if you have one for Brenda or for Gary, I'd encourage you to get those to them. So again, that's all the time that we have today. Please join me in thanking Gary Bell and Brenda Quinlan for their presentation, as well as our sponsors, our sponsor, DCS. If you have additional questions or comments, please don't hesitate to click on the Email Us button on the console. Please visit webinars.qualitymag.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time, and we hope you found this webinar to be a valuable experience. Have a great day.